I was staring at a silent data stream when one impossible spike appeared, and in that moment, the moon stopped being quiet. They say the moon has no surprises left, but what James Webb saw didn't look ancient or calm. It looked sudden, violent, and wrong, like something had just slammed into our closest neighbor while no one was watching.
I remember the exact second my breath caught, because space is usually patient, predictable, and brutally honest, and yet what unfolded on my screen felt like a secret being ripped open. I work with deep space data every day, signals stretched thin across billions of kilometers, light that has traveled longer than any human life, and James Webb was built for that kind of truth. Webb was never meant to watch the moon. It was designed to look outward, past Mars, past Jupiter, past the edges of our solar system, to see the first galaxies ignite after the Big Bang. But sometimes, when you calibrate an eye powerful enough to see the dawn of time, it notices things closer to home. What Webb recorded wasn't an image in the way people imagine photographs. It was a sudden, sharp infrared anomaly, a brief bloom of heat where none should have been, appearing along the moon's shadowed limb. The moon, airless and cold, doesn't flare without reason. No weather, no tectonic plates, no hidden volcanoes waiting to erupt. When heat appears there, something has happened. Something fast, something violent. And in that instant, every routine assumption we had about background noise collapsed. I leaned back and thought about how the moon is constantly under fire. Micrometeoroids rain down every day, grains of dust traveling faster than rifle bullets, punching invisible scars into the regolith. Larger impacts happen too, flashes sometimes caught by amateur telescopes on Earth, quick white sparks on a black surface. But this was different. This was infrared energy detected by the most sensitive space observatory ever launched, sitting nearly 1.5 million kilometers away at the second Lagrange point, unfolding its golden mirrors in the cold darkness. Webb doesn't blink unless something truly changes. My mind went immediately to the numbers. Impact velocity, thermal signature, duration. The spike rose and vanished quickly, consistent with a high-speed collision releasing heat in a vacuum, then dissipating into the endless cold. But the energy profile was strange, sharper than typical micrometeoroid events we've modeled. That's when the word mysterious began circulating quietly, not in headlines, but in private messages between scientists who know better than to jump to conclusions and yet couldn't ignore the data. As I stared at that anomaly, I thought about Artemis, about how NASA plans to return humans to the moon, to build a sustained presence near the South Pole, where water ice hides in permanently shadowed craters. Astronauts will walk where no human has stood, trusting the moon to be stable, predictable, safe enough. And here we were, reminded that space doesn't care about our schedules. The moon may look frozen in time, but it's still part of a dynamic, violent system, sharing Earth's neighborhood with debris left over from planetary formation. I imagined standing on the lunar surface when it happened. No sound because there is no air. No warning because there is no sky to watch. Just a sudden flash in the distance, a silent explosion of light and heat, followed by dust arcing upward in perfect, slow motion, grains rising and falling like a ghostly fountain under 1/6 gravity. That is what an impact looks like on the moon, beautiful and terrifying, a reminder that even the most familiar celestial body is not domesticated. What unsettled me most wasn't the idea of an impact itself, but what we didn't immediately know. What was the object? A fragment of an asteroid, a fast-moving meteoroid from a known stream, or something rarer, something we don't track well because it's small, dark, and nearly invisible until it hits. Webb's detection didn't tell us size or composition directly, only that energy had been released where cold should reign. And in space science, gaps in understanding are where the fear and the excitement live. James Webb is an infrared telescope, meaning it sees heat, not visible light. That makes it uniquely sensitive to transient events, things that glow briefly before fading back into darkness. While it isn't designed as a planetary defense system, its instruments are honest. They don't care what we expect to see. They record what happens. And that night, what happened was a reminder that the moon is still being shaped, still taking hits, still writing its story one collision at a time. As the data was cross-checked, compared with lunar monitoring programs and Earth-based observations, I felt that familiar tension build, the space between discovery and explanation. This is where history lives. Before we name it, before we understand it, before we turn mystery into math. Somewhere on the moon's surface, a new crater may exist, fresh and sharp, its edges unsoftened by time, waiting for future orbiters, or maybe even Artemis astronauts, to find it. And as I watched that infrared spike fade into normalcy, I realized something unsettlingly simple. The moon didn't suddenly become dangerous. It always was. We just noticed. And noticing changes everything. The waiting is always the hardest part, because space never answers immediately. After the initial detection, the room fell into a strange quiet, the kind where no one speaks because every word might be proven wrong by the next data packet. I remember refreshing the telemetry again and again, watching as James Webb continued its scheduled observations, utterly indifferent to the human anxiety wrapped around its findings. Out there, near the L2 point, Webb simply did what it was built to do: collect truth, no matter how inconvenient that truth might be. We began ruling things out, one careful assumption at a time. It wasn't a spacecraft impact. Every human-made object near the moon is tracked obsessively, its orbit calculated to the decimal. No scheduled missions, no spent rocket stages, no debris should have been anywhere near that location. That narrowed the field to natural objects, the ancient leftovers of a solar system that never quite finished cleaning up after itself. Asteroids, comets, meteoroids, most of them harmless. Most of them invisible until they announce themselves in fire. I pulled up old lunar impact studies, decades of research showing how often the moon is struck. The moon has no atmosphere to burn things up, no shield like Earth's sky. Everything that comes in hits hard. NASA scientists have estimated that objects the size of a softball strike the moon roughly once a week, releasing energy equivalent to small explosions. But the thermal signal Webb caught suggested something faster, hotter, or compositionally different. That's when the conversations became more cautious, more deliberate. When scientists stop using confident language, you know something doesn't quite fit. I couldn't stop thinking about how James Webb wasn't even supposed to be watching the moon. Its sun shield keeps it permanently cold, its mirrors aligned to study distant galaxies and exoplanets. Yet here it was, accidentally becoming a witness to violence in our own cosmic backyard. That irony sat heavy with me. We built a telescope to look back in time, and it ended up telling us something about the present, something immediate and raw. Follow-up observations began almost at once. Lunar Reconnaissance Orbiter data was requested. Earth-based telescopes were alerted. Even amateur astronomers scattered across the planet became part of the search, combing through footage of the moon from the hours surrounding the event, hoping someone, somewhere, caught a visible flash. This is how modern space science works, not in isolation, but as a global nervous system, responding to unexpected stimuli. As the analysis deepened, one possibility kept resurfacing in my mind: interplanetary debris. Not the slow, predictable stuff we map and model, but fast-moving fragments flung inward by gravitational interactions with Jupiter or debris shed by long-period comets diving toward the sun. These objects can strike at incredible speeds, carrying more energy than their size suggests. If that's what hit the moon, then Webb may have detected something we rarely see so clearly: a high-velocity impact that briefly turned cold rock into glowing heat. I imagined the moment of contact: a black sky, a lifeless plane. Then, in less than a second, kinetic energy converted into heat, the surface vaporizing, plasma blooming outward, dust lifting into the vacuum. No roar, no shockwave, just physics, ruthless and elegant. That flash of infrared light was the moon screaming silently, and James Webb happened to be listening. What unsettled me most was how this tied into humanity's future plans. Artemis isn't a distant dream anymore. Rockets have already flown. Hardware is being tested. Astronauts are training. We talk about permanent lunar bases, about mining ice, about using the moon as a stepping stone to Mars. And yet events like this remind us that space does not pause for our ambitions. The moon is safer than many places in the solar system, but it is not safe. It is active in its own quiet way, constantly reshaped by impacts we barely notice. As more data came in, confidence grew that this was indeed a natural impact, not a malfunction, not a sensor glitch. The thermal signature was real. The timing was real. Somewhere on the moon, a scar had formed, one more line etched into a surface that serves as the solar system's memory. Unlike Earth, which erases its wounds through erosion and weather, the moon keeps its scars forever. That crater will likely still be there millions of years from now, long after our species has changed beyond recognition. I found myself staring at images of the moon taken decades ago, wondering if future comparisons would reveal a tiny new mark, a fresh blemish born in a fraction of a second. This is how discovery often feels, not like fireworks, but like standing at the edge of something unfinished. We had answers, but not all of them. We knew something hit the moon. We didn't yet know exactly what or what it might teach us. And beneath all the analysis, one thought lingered. If James Webb can catch something like this by accident, what else is happening in our cosmic neighborhood that we haven't noticed yet? What flashes of heat? What silent impacts? What warnings written in light, waiting for us to look in the right direction? As the days passed, the mystery refused to fade, and that, more than anything, told me it mattered. In space science, most anomalies die quickly under scrutiny. They dissolve into calibration errors, timing offsets, or misunderstood reflections. This one didn't. Every time we tried to explain it away, the numbers held their ground. The signal stayed sharp. The location stayed consistent. The moon had been hit, and the universe had left us a receipt. I began thinking less like a technician and more like a witness. James Webb had effectively caught a crime scene in thermal light, a fleeting heat bloom on a body we've stared at for all of human history. The moon has guided travelers, inspired myths, and shaped tides, yet it remains vulnerable, exposed, endlessly patient as the solar system throws debris at it. This impact wasn't just data. It was a reminder of how thin the line is between stability and chaos. New simulations were run, modeling impactors of different sizes and compositions. Rocky asteroids, metallic fragments, carbon-rich debris left over from comet tails. Each scenario produced a slightly different thermal curve, and when we overlaid them with Webb's data, a pattern began to emerge. The best match suggested an object smaller than a car, but moving so fast that it released energy disproportionate to its size. Speed, not mass, had done the damage. That realization sent a chill through me, because fast objects are the hardest to see coming. I thought about planetary defense, about how Earth relies on its atmosphere as a shield, burning most incoming objects to dust. The moon has no such luxury. Every impact is direct, uncompromised. In a strange way, the moon protects us by being hit first, by recording the history of near-Earth space in scars and craters. Webb's detection wasn't just about the moon. It was a data point about our environment, about the traffic patterns of debris that share our orbit around the sun. What made this event even more compelling was timing. The impact occurred during a period of increased meteoroid activity, when Earth, and the moon along with it, was passing through denser streams of interplanetary material. Most of that material is harmless, but streams are messy, unpredictable. One slightly larger fragment, one with the wrong trajectory, and you get a flash on the moon that catches the eye of a billion-dollar telescope designed to look elsewhere. I imagined future Artemis astronauts standing on the lunar surface, looking up at a black sky filled with stars, knowing that above them, unseen, objects are constantly crossing paths with the moon. Would they feel fear, or would they feel awe? Would this knowledge make the moon seem hostile or alive in a way we've never fully appreciated? I suspect it would do both. As the scientific community began preparing a formal analysis, I felt that familiar blend of humility and excitement. We hadn't discovered aliens. We hadn't rewritten physics. But we had witnessed a moment, a brief, violent interaction in space, and understood it better than we ever could have a generation ago. That is the quiet power of instruments like James Webb. They don't just answer the questions we ask. They reveal the questions we didn't know to ask. The moon has always felt constant, unchanging, a symbol of permanence in an unstable universe. And yet, Webb reminded us that permanence is an illusion. Everything moves. Everything collides. Everything changes, even if it takes millions of years for us to notice. That impact was a punctuation mark in the moon's long story, and for a brief moment, we were there to see it happen. I closed my screen that night with a strange sense of gratitude, not because something had crashed into the moon, but because we noticed, because we were finally building eyes sharp enough to see our cosmic neighborhood not as a static backdrop, but as a living, moving system. And once you see that, you can never look at the moon the same way again. The more I thought about it, the more I realized this moment was bigger than a single impact. It was about perspective. For most of human history, the moon has been a constant presence, rising and setting with reassuring regularity. Wars ended. Civilizations collapsed. The moon stayed. And yet, James Webb showed us something that shattered that quiet illusion. Stability in space is not stillness. It is motion balanced on a knife's edge. As reports circulated internally, a careful language began to form. No sensational claims. No dramatic headlines. Just measured words describing an unexpected thermal event consistent with a high-energy impact. But behind those calm phrases was a current of excitement I could feel in every conversation. This was a reminder of why we explore, why we build instruments that can see the universe in ways our eyes never could. Because sometimes discovery doesn't arrive on schedule. It arrives uninvited. I kept returning to the role of infrared astronomy. Visible light tells us how things look. Infrared tells us how they behave. Heat is honesty in space. You can't fake it. When something releases energy, infrared instruments notice, whether it's a newborn star igniting, an exoplanet glowing under alien suns, or a sudden flash on the moon. Webb's detection placed the moon briefly in the same category as those distant, dramatic events, a participant in cosmic processes rather than a passive observer. This led to a deeper question, one that lingered long after the data was analyzed. How many events like this have we missed? Before Webb, before modern lunar orbiters, before global networks of telescopes. For billions of years, the moon has been struck again and again, each impact rewriting its surface. Only now are we becoming capable of watching those changes in near real time. Only now are we realizing how dynamic, even quiet, space truly is. The implications for future missions were subtle but profound. If we can detect impacts thermally, we can improve our models. We can predict risk. We can design habitats with shielding informed not just by theory, but by observation. Artemis is not just about returning to the moon. It's about staying. And staying means understanding the environment down to its rare but violent events. That single infrared spike contributed to that understanding more than people might realize. I found myself imagining a future briefing, years from now, where astronauts are shown a map of recent lunar impacts before stepping onto the surface. Not as a warning meant to scare, but as knowledge meant to empower. This happened here. This is how often. This is what space does. The moon will never be entirely safe, but neither is Earth. The difference is that on the moon, the risks are honest. There is no atmosphere pretending to protect you. There is only physics. Emotion crept in when I least expected it. Not fear, but awe. The idea that a telescope built to see the first light of the universe also witnessed a moment of destruction so close to home felt poetic. Creation and collision, birth and impact, all part of the same story. The universe doesn't separate them. It lets them coexist. As the mystery settled into understanding, one final thought refused to leave me. This wasn't a warning. It was an invitation. An invitation to pay attention, to look not just outward but around, to treat the moon not as a dead rock, but as an active participant in our shared cosmic neighborhood. Because when you start seeing the moon that way, every crater becomes a sentence, every impact a word, every observation a chance to read the story more clearly. By the time everything's settled, by the time the anomaly had a name and a classification and a paragraph and a technical report, I realized something important had changed in me. The moon no longer felt like a background object. It felt present, alive in its own stark, silent way. That single detection by James Webb didn't just add data to a spreadsheet. It reshaped how I understood our place in space. We like to think exploration happens far away, beyond Mars, beyond Saturn, in places so distant they feel disconnected from daily life. But this event proved the opposite. Space is not out there. It is here. It is active. It is interacting with us constantly. The moon, hanging above our cities and oceans, is not just watching history unfold. It is still being written upon. I imagined future generations watching replays of this moment, seeing how casually it began. A small spike, a brief glow, no alarms, no countdown, just a quiet reminder that the universe doesn't announce itself. It acts, and if we're paying attention, we learn. James Webb paid attention, and through it, so did we. There's comfort in knowing we are finally developing the tools to see reality as it is, not as we wish it to be. The moon will continue to be struck. Asteroids will continue to pass. Debris will continue to wander. But now, we can observe, analyze, and prepare. Knowledge doesn't eliminate risk, but it transforms fear into understanding. As I looked up at the moon that night, brighter than usual against a clear sky, I felt a strange sense of connection. Somewhere up there, a fresh crater rested in shadow, still warm once, now cold again, waiting to be found. A silent mark of a moment James Webb noticed, and history recorded. The moon didn't change that night. We did, and that is the real discovery.